All right, welcome to the October 2016 Structural Modeling Video Conference. Today we're working on the new Google Hangout interface, which I've been told works the same on the broadcast receiving end, but it works quite differently on the setup end for the person that's setting up these broadcasts and managing them. That whole management interface has changed at least a couple times in the last month. Due to that effect, I had to schedule 2 or 3 different events for today. Now, hopefully 2 of those I marked private so that no one can see them because I couldn't figure out how to delete them. And then we have this one, which is public and being broadcast and recorded for everyone. So if you had trouble and couldn't figure out how to log on, hopefully next month we'll have this all figured out. So again, software changes, things are always changing, difficult to figure out and get it right the first time. So we've had an interesting progress this month. And one of the primary things that happened this month was when I was looking for specific user requirements for structural modeling software, I ran across a person in Ireland who was published in Psychology Today, an article about Warfield's work in structural modeling 40 years ago. It appears that the upshot of that is essentially the structural modeling and interactive management and interpretive structural modeling approach is a way of addressing collective intelligence and figuring out and learning new things together as a group online and infusing logic and a number of aspects that are not available in other types of approaches today, especially ones that are computer-based. So it'll be interesting to see how that work unfolds, and if we find any common interfaces with that group. I think the psychologists are very important in calibrating people's understanding of the words and the semantics and the context within which we perform these activities. So if there is an interface developed there and there's some joint interest, that would just be great. So let's see, then we have the read ahead document for this month. I'll bring that up and share it right now. Let's see first. Okay, we got that. Now we'll go ahead and find the read ahead document. Let's see, I think this is it right here. Let's see if this is it. This is it. Okay, so make it a little bigger. All right, so where we are in the process of developing these techniques and the software to support the interpretive structural modeling, and interactive management techniques. We're getting close to the end of the exploration phase where we've been looking at different software implementations and different software approaches. One of the aspects that was discovered during this search is that they have most all the software, if not all the software, is closed source. All the existing software for this particular activity is closed source. The software that we're developing is the only open source software that we know of. So if anyone else has open source software or has closed source software that they'd like to open up and discuss and turn loose to the community for community use, that would be great. But so far right now, this particular activity is the only open source software activity that we know of. And then secondly, the open source software and the lack of transparency of what the software does creates some very difficult situations for system scientists who really want to work in this area. And the fundamental problem with that is that scientific publishing should be based on the fact that a scientist does their work, they describe what they did, they describe their methods, processes, and results, and then other scientists see if it's reproducible, see if they can reproduce those results, understand the process, verify, validate basically that yes, this is something that actually we also observe this phenomenon. With structural modeling that has a core component of software that runs on a digital computer, to fully understand what impact and what the processes are and what the scientific basis for the outcomes, you really must have access to all of the algorithms and all of the methods that are being implemented by the software. Closed source software does not let you do that. In our structured review technique that Kevin Dye proposed and looked at extensively, look at the literature of ISM and other types of structural modeling activities, we found that it was difficult, if not impossible, to really determine what the processes were and very difficult, if not impossible, to reproduce the results due to the lack of open source software. So the structured review has been pared down a little bit. I'm not quite sure what Kevin's views are on that right now, but essentially open source software that's available for everyone, everybody can look at it, read it, understand it, would, I believe, be a great benefit to the community, especially the system science community that wishes to verify and validate reproducible results in this area. So as we go forward and think about the architecture, the functions, and the applications for structural modeling software and structural modeling events, like what role does the software play, what role does the facilitator play, what role does the organization play in these events, it becomes important, I believe, to historically determine the best source of specific information you can find, build on that, so there's some connection to what's already been done, try to increase the fidelity and the usefulness and utility of that information by making clear incremental steps or additions to the existing body of work, and do that and present it to the community in a way that the community can evaluate it and say whether or not it appears to be valid. So when we started looking at this specific aspect of how can we look at the historical data and how can we present it in a way that's verifiable and reproducible, we ran into some uncertainty about language and logical models. So the abstract relation type and the augmented model exchange isomorphism were both developed to address a more specific methods for communication and more specific semantics about the logical situation and about the logical relationships that are present in the current system. Now that we've done this, and the AMEI and the ART construct have been out for comment for a couple of years, we're now started to apply these in with the analysis of historical documents. So the first historical document that we're going to look at today that relates directly to software and software architecture is the Handbook for Interactive Management. This is, I believe, the appendix of the Handbook for Interactive Management, second edition, 1994, where there's a description of the functions and capability of the George Mason University Interpretive Structural Modeling software. As we look at that, there's essentially three software commands, basic system structuring commands: the do model, the do clus, which is doing clustering, and the do priority. So when we look at this and read the description in the handbook, essentially do priority requires structuring in a model. It's structured with an asymmetric type of logical property with the structuring relationship, and to be irreflexive and transitive. Also, in the do priority, in that system within the GMU software, it's allowed to have only one item of priority at each level, or you can have more than one item of priority at each level. So the do priority command basically is has been reproduced in the open source software that we've published over the last couple of years. The strict ordering component of the software, the web application that we published, allows only one item in the priority at each level. So if you're working with a group and you want them to prioritize a set of actions or ideas or elements, you want to force the group to make distinctions between each element, meaning that each element, there can be only one element associated with a priority. Two elements cannot have the same priority. So that would be the strict ordering. Now in the GMU ISM software, they don't make this. Well, I believe you can make the priority system work that way, but it's not enforced. There's not a command that says, oh, it has to be strict. And so what I believe the next steps that we're going to do with our software is we're going to start with this very simple ordering priority approach. We'll do a strict ordering system that only allows one element or object at each level of priority. And we'll create another one that basically allows more than one element of priority at each level. And then we will package these as specific functions so that when you start an activity and your goal is to prioritize every element with its own priority, that no two elements can have the same, then you would use one function or one approach. And then if you wanted to allow more than one element to have the same priority, then you would use the other approach. It's just basically our next step at not only documenting these commands and what they do and how they would be applied, but also our next step at developing the user interface and making it more understandable. The interface we have right now is rather cryptic and sparse, so we're going to be focusing on these very specific steps and packaging those pieces of software for specific functions, starting with the do priority commands that are basically detailed here in the handbook from 1994. The do cluster command basically requires a symmetric logical property in the system structuring relationship. So this is is presented as a method where you're going to identify groups of things that are the same. You're going to be categorizing. You're going to be putting things into categories. And this particular command is named do cluster, but it could be also as easily have been named do category. So we're going to put things in the same categories. They're symmetric, they're equal. So that will be another one of the interfaces that we'll put together and package that up so that when you're categorizing things or clustering things within a large group of people, it's very clear that what the steps are and what happens next. So that will actually be like, you can have three specific interfaces right there. One with a priority type structure that only allows one element of priority at each level. A priority structure allows more than one element of priority at each level. And then the do clustering and the do categorization that allows you to cluster things or categorize elements in a group. The do model basically right now is one aspect that we're working on. We're working on not only the interface and what that would look like, how you would perform that, but we're also thinking about the mathematics and the algorithms, the architecture, software architecture behind that. I had a fairly good discussion with Kevin Dye later last week, and Kevin had some really good observations about these three models, or these three commands, and he also had some very good observations about what we might be able to do with the do model. So we'll work on that and see if we can make some progress by next month. And hopefully by next month we'll have some of these basic approaches packaged into specific individual types of software units, so that it'll be clear what the process is associated with each command or each approach, and some guidelines of how they may be applied. And then we'll kind of work that out. Okay, let's see, where are we here? So as it goes ahead into the read ahead document, we talked about a little bit about why we developed the AMEI and why we developed the ART construct. But one of the more interesting outcomes of this specific analysis is the treatment of the adjacent natural language structuring relationship. And there's a couple of really strong themes that are associated with this kind of, it seems almost trivial event. But there's the work that was done by Warfield. He used the adjacent natural language relationship to describe what he called transitive closure. So the first aspect of that approach is the fact that I personally don't see the adjacent natural language relationship as being transitive. I think of adjacency as being intransitive. But then as you read more of Warfield's work, you find that he actually uses another natural language system structure relationship called immediately adjacent to indicate an intransitive natural logical property. So there's, within a group of human beings that are being asked to use the natural language term adjacent to structure things, there's going to be some individual conflict to their background and their way they think about the logical properties associated with the natural language term adjacent. But what's obviously required here is some type of test, kind of quick test that the individuals that are involved in the activity can take, and so that they can kind of normalize their understanding of the natural language structure and relationship logical properties and make sure that they agree. Because without that fundamental agreement, not only the modeling activity, but the outcome of the modeling activity will be highly suspect, because there's the fundamental basis, the logical properties that are being used are not commonly understood. So there'll be a tremendous amount of uncertainty and a tremendous amount of confusion. So essentially here then, brings out the point that there really needs to have some type of activity that works with a group of people so we can all normalize and understand our different views of logical properties. And that is an area that I think is completely wide open. I haven't looked into it too much, but it's an area that ripe for research and exploration. And I believe it's fundamental to supporting the type of interpretive structural modeling or structural modeling activities. We really need to have a solid understanding of how we can determine if everybody is using the same type of logical property. So that's a key indicator of just one aspect of the adjacency natural language relationship. Another aspect of the adjacency natural language relationship is the fact that the way Warfield presented the work in his Battelle monographs was in relationship to mathematical forms. For example, like with a priority. So with a priority asymmetrical type of structuring relationship, he would talk about a priority matrix. Or when he was talking about events that precede or succeed each other, he would talk about basically a precedence type of matrix. And so the natural language relationship then was coupled with the idea of a matrix, because that's how Warfield encoded the information in his Battelle monographs. Unfortunately, the mathematics community has a very different meaning for an adjacency matrix. And just this presentation and confusion about what an adjacency matrix is, whether you're using the natural language relationship to structure a matrix, or are you talking about the mathematical form of adjacency matrix, also generated a lot of confusion. that's one of the themes that I've been researching and pulling those threads through some of the earlier literature, and we'll talk a little bit more about that later on, and try to start sorting some of these things out and to show where some of the confusion is and highlight some of the areas that can be ameliorated and then make this a more commonly understood approach. So I believe there's been a lot of literature published on interpretive structural modeling that's suspect just because of the determination and the semantics associated with the term adjacency matrix. It's not clear whether you're talking about the mathematical term or whether you're talking about the natural language term. That's another area that needs to be explored. You have to develop a convention so it's very clear which one we're talking about and reduce that uncertainty by creating well-known rules that everybody understands. Okay, so now, to me anyway, the most interesting outcome of this idea of adjacency, and adjacency being either intransitive or transitive, is the fact that the modifier for immediately adjacent, the Warfield used adjacent to say, okay, that's transitive. Immediately adjacent is intransitive. So what we've done, what's happened here is you've modified the natural language relationship, some kind of modifier on it, and it changes the logical property. In this particular case, it changes it from transitive to intransitive for everything, for the whole scope of the logical property operator. However, this points out an application where you could actually design a system that said, well, it's transitive for 6 units, or it's transitive for 7 or 8 units, or something like that, to have some function that says, oh, the scope of this natural language relationship is determined by this scope function. And so once you start thinking about this idea of, oh, we can have these matrices that have a natural language structuring relationship that can have limited scope, and that scope basically is limited by, contextual modifiers, local modifiers, global modifiers about what's going on, then you can see that there's a possibility that these matrices that are basically static 0, 1, and binary, which are good, you can have those to determine a structure in certain ways, but then you can also take those and start thinking about them more as a combination of neural networks or fuzzy systems, something that has a varying type of value, not just 0 and 1, but something in between. And so within the abstract relation type concept, where we allow many different matrices and value systems and structures to be put together, each different matrix within those combinations could have different scoping rules, could have different logical rules, they could have different global rules to be evaluated in the global context and again modified there, so that you have a more adaptive type of system. And so the ART construct was really designed to be a very general type of approach that would allow you to integrate and use almost any type of mathematics that's necessary to achieve your goals. And we believe that fundamentally the idea of binding scope for a logical property is much like the membership function for a fuzzy number, or the basis of the percent firing on the neural net node, a number of other types of activities, so that these ideas, I believe, can be implemented in a way to help us more effectively look at natural language interpretation and interpretation from a group. So that's those are the really interesting things that came out of this fairly innocuous idea of, oh, what is an adjacency matrix? So the idea of modification. First of all, we had the idea that, oh, adjacency, adjacent to, was determined as transitive by Warfield. And that personally, it took me a long time to figure out that that's what he was doing. I never would think of adjacent as being transitive. So I would always think of it as intransitive. So we need some type of psychological tests or some type of quick tests for people to understand and get a understanding whether or not the whole group is looking at these logical properties in the same way. And if they're not, then what needs to be adjusted? So there's definitely a whole area there that would need to be looked at. The outcome of that work would be an increased type of understanding, or an increased, not validity so much, but just give you more comfortable feeling about what you're doing. That, oh yes, everybody's kind of talking about the same thing. So there's a psychological interpretation factor of the word. Second thing that happens here is the conflict between mathematical term and the natural language term. This conflict is clear in the literature. There's a number of authors, a couple of them very prominent authors that essentially in this specific aspect brought in a lot of confusion. So there's an area there that I think there's a clear pathway to sort it out now. And we can sort that out now using the graphs and this type of more high density type of evaluation of what's going on. Then of course, the idea of the limited scoping, not just having a logical property apply or not apply, but to actually have a gradation or allow different types of patterns within the logical property, which gets you into a much more adaptive type of approach. Some work has been done in this area. I know that there's some work that was done in Japan, I believe, on fuzzy ISM and some other work. I'm not quite sure that it had the idea of a limited scope involved, but anyway, there's a lot of potential here for this type of activity. So Mary, do you have any questions, comments, observations?
At this point, I don't. I believe, though, that it would be interesting to go ahead and discuss the transitive embedding algorithm implications there.
The transitive embedding?
Yes.
Okay. All right, so let's go back and look at the do model. Haven't really put the specific information and details of the transitive embedding into documents for this discussion, but it can be found in the Mathematics of Structure that was excerpted from the Societal Systems books, Societal Systems, Planning, Policy, and Complexity. And let's...
Pardon me just a moment.
Sure.
I was actually talking about addressing the next to last paragraph in the read ahead,
The
where
next
you're
to last
talking about
paragraph. Okay.
where you're talking about the transitive embedding.
Software. Oh, okay. All
And
right.
that takes you to the same
Yeah,
place.
it's the same thing. It's the same thing. It's just a little more. I'm going to add a little more background to that specific part. The
Good, thank you.
yeah. So on the GMU ISM software and in the analysis of these algorithms and the basic structural modeling mathematics that was done by Warfield, there's the idea that you have a matrix, you have one matrix, you have one situation, and you get a group together, you run your process, and you start structuring that matrix. You start structuring that system. There's also another process where if you have two systems that have already been initially structured and they do not have any common elements and they are structured on the same natural language relationship, then you can couple those together. And that's the coupling method of the transitive embedding. And it's very powerful because you can get some efficiencies in logical determination. You can get some efficiencies in logical types of insight into this large structure. A key problem with the transitive embedding algorithm as developed by Warfield was you have to have two previously structured matrices. So when you start, you've got a brand new system and you want to use and take advantage of these logical efficiencies of transitive embedding, you really can't because nothing is structured. So there's a couple of different ways to approach that. One way is called the scanning method, where you take your unknown system structure, you're just starting out, and you go through and you just scan through each element and get some preliminary information on each specific element. Then, from that preliminary information, you structure that matrix in a rather non-complete way, and then you break it in two, and then use that thing that you've broken in two as the two matrices to apply the transitive embedding algorithm. We're looking at that right now and comparing that to how we do our matrices by dynamically adapting the matrix. There's some very similar aspects going on. The matrix approach that Warfield used had basically a static matrix form. And we use a more of a dynamic type of approach. So it's going to be very interesting to see how that works and to take it out further. But this applies directly to the complete general model. And we need to look at that and get a lot more input on that. So we're going to be actually comparing our algorithm and approach to what else was going to the transitive embedding method. That make sense?
It does make sense, particularly from the perspective of looking at a set of objects where you understand or have the relationship, but you have not yet done any structuring. However, if you take the transitive embedding algorithm, can it be applied, as you say, to several sets of information that you have already organized, and then found that you're addressing the same, as you call it, natural language relationship or function? Is that the same thing that they are doing in Japan, related to the physical systems?
Oh, my Japanese isn't that good. But there appears to be some similarities. Okay.
Thank you.
But let's see. What I was thinking about here basically is there's a number of different things going on. And the first thing about transitive embedding algorithm is efficiency. In fact, leveraging the logical properties really is about efficiency. You can get this information by empirical data gathering. You can do that, but it's expensive. And with these larger systems that have all these different interconnections, it becomes cost prohibitive to even think about doing that, right? So this becomes a cost trade-off. And so when we say, okay, we want to use the logical efficiencies and cost reduction that's associated with the logical insights that we get from the transitive embedding algorithm, say, okay, how do we do that? Because when we just started, we don't have anything. So when you've just started, you've got to just go get data. And then as you get data, you can say, well, what's the smartest, most effective, cost-effective way for me to get this data? And we have an approach that we're using. It's a little dynamic and uses some basic searching and sorting algorithms. The transitive embedding algorithm done by Warfield is kind of static, but it has some very positive types of logical cost reduction potential. And so really you can do all of these activities if you have enough time and money without any logical inference. But most people don't have that kind of time and money on a huge system. And so what's the effect and the function of these particular logical inferences is to allow you to engage large-scale systems in a way that you couldn't do before. So that's kind of the main thing going on. And with the fellow that published in the Psychology Today, you know, the people they're looking at today, what we have is these huge, massive amounts of data that nobody can really understand what's going on with them. We just got this huge machine, we got all these huge data piles and stuff. But how do we get real information and knowledge out of those huge data piles? People are beginning to believe that there's fundamentally something about Warfield's approach that will allow them to do that and to actually enable collective intelligence. And what it means is we really need, as a group of people, to come to some type of understanding or insight. And to do that, we need to have effective methods. So that's what that is all about.
Thank you.
Yeah, you're welcome. Okay, so let's go back here and check the, you can check the agenda and see if I have, okay, I think this is the agenda. Let's look at this again. Okay, yeah, the agenda. We've got about 15 more minutes, so we'll have an update on the systematic review process. Kevin probably is having trouble figuring out how to connect. This new interface is not as easy anyway for me as the other one was. Hopefully we'll get it figured out in the next few months. So there's still there's been no input for a joint project for NCOSE IW. Mary and I have 2 papers in process for NCOSE 2017. And there is a possibility of another one, but I'm not quite sure what's going on there. I haven't heard anything back on it. And then systematic review team formalization. I'm not sure where Kevin is on that. I think where he is the there's just not enough systematic information out there for us to review. So we have a lot of things to do there. One thing I haven't done is I haven't discussed the SMP web application update. So let me go ahead and bring that up and show some of the particular items that are happening here. Okay, so basically we have a fundamental set of software now that allows us to display and to deal with essentially the do priority and the do cluster type of commands in a fairly effective way. We need to work on the interface. The interface is kind of cryptic, so it doesn't really guide you through it unless you know exactly what's going on. Kevin had some good ideas about that, so I'll be working on those. But what you're going to see next is I'm going to run through very fast a series of visual tests that are all programmed to drive the browser and to make sure that the system works. So this is just the system tests or visual tests that we use to make sure that it's all automated, everything's working well. You can kind of see this walking through it. This is a kind of a step at a time work down through the search. It's really just not a binary search or anything else. It's just a really non-intelligent search, let's put it that way. So the search elements can be increased in efficiency by using binary search in our approach, and we believe the binary search will kind of be the same, and maybe get the same effects as the transitive embedding. And we're hoping that we can use those basic computer software concepts to introduce this material to people that are familiar with computer science algorithms. So here's another run. I've slowed this down a little bit so you can kind of see what's going on. In this particular case, we're allowing items to be equal. So you can see that down at the bottom, right down here, we've got 3 and 6 are the same, 7 and 9 are the same, 8, 11, and 12 are the same. So they're kind of an equivalency. And as you can see, we started at the top. We're just going one at a time through this specific search. We're not using any advanced searching techniques or anything else. We're just going through them one at a time in a very unintelligent way, let's say. So binary search would probably be more efficient. I've already ran a couple of those. They turn out to be at least twice as efficient, let's put it that way. I'll get some more of those up online and with details later on. And so you can see that essentially this goes through, orders the system, and then it's basically done. Now we're going to do another one. In this particular one, I believe we don't allow things to be the same. So it's a strict order. And we start up here in the upper left-hand corner, start working our way down. But what happens, of course, is the items in the top left-hand corner then start to become structured. They start to become ordered. So everything that is green and blue is ordered in some fashion, and all the yellows below it are unordered. And this is kind of like the transitive embedding approach, where you take a scan through it and you kind of order it, but it's not really ordered. And then you have to do it again and again before you do the coupling. Well, we just do that by do something similar by ordering the items in the upper, well, in the left-hand top lower triangular area. As you can see now that as they're ordering more things in this top, like the 7 and the 4 and the 2 and the 1 and the 8, they're stable now. They're kind of ordered in a way that seem to be pretty stable. Okay, 17 is going up though. 17 is going to go up. Okay, it goes to now. 17 is in the third slot, right? So then that's stabilized again. See how far 18 goes up. Well, 18, yep, only goes up there. So this whole section above it now becomes pretty stable. So you could actually use binary search instead of doing them one at a time. And it would reduce then the amount of empirical data you'd have to collect. We're going to be looking at that and seeing what kind of efficiencies we can get in general. Right now, it looks to me like with the binary search, we can do at least cut the number of required information in half. And of course, it all depends upon the structure of the original data. So if it's completely inversely ordered or something like that, it's going to be more. But if it's randomly distributed, it should be okay. Of course, you see this time we took the 22 all the way up there. And so just doing them one at a time. Okay, so that's going to get a graphical understanding of what the algorithm is doing. In this particular case, we're having, it's like everything, well, no, we have different levels. Okay, there we go. And then here, let's see, we have, looks like everything at the same level, right? So everything is a 2 there. And we'll go back, we'll look at this one again. Again, we're just walking through this one at a time. A very expensive type of search, but you get an idea of what the baseline is and how you can improve it. Also, the information we have about the global system when it's done. We know in the upper triangular, there'll be all zeros. We know in the lower triangular, they'll all be ones. And so knowing that global information is important, because it allows us to effectively make decisions about efficiency in the logical approach. And this is just a very simple example of how a global information, we know when we're done, everything's in the upper triangular is 0, everything in the bottom triangular is 1. Very simple type of activity that would let you know that, you can change states. Let's say you had a number of these matrices, and I said, okay, well, when this matrix gets to a state where everything in the bottom 1 is 1s and everything in the top is 0s, then this all collapses into a single node in a higher level global system. Those are the types of things that can happen with systems that allow different kinds of binding relationships. So we're getting close to the end here. There's one more one thing I'd like to look at, and that is a specific document that was, I think, done by Ben Broom on collaborative systems. So I sent this out, and it's kind of an interesting document. It has the 5 steps. And again, what we start off with talking about decades of research in social psychology and cognitive science. Highlight the many limitations of group problem solving. So that's kind of a key factor. We've talked about some of the things that might contribute to that today, but what we have now is in this particular document, we have 5 easy steps. And along with these 5 easy steps, we have screenshots of software that do that. So we look at this 5 easy steps, identify the trigger question that prompts creative ideas from the group members. Step 1. Step 2 is identify the key stakeholders who will come together as part of the working group. Step 3 is record all the ideas generated by the group in response to the trigger question. Step 4 is individual group members vote to select the most important ideas, and votes are aggregated across the group to produce a consensus set. And step 5, structure selected ideas to produce consensus model. So mostly what we've been working on so far is step 5, the structuring component, the mathematics and what's going on there. So we're going to start working on developing and looking at the other 4 steps, steps 1 through 4. And anyone that's interested in that area, please let us know, because we would like to get as many interested people as possible focused on creating an open source set of software that will implement and support this type of collective activity. It's amazing to me that after 40 years of time, people are still going back to Warfield's work and saying it's what we need to do. And after 40 years, it's amazing to me that we really don't have any open source software or a process by which there's consensus about what that really means at a fundamental level. So there's appears to be tremendous demand for these concepts and approaches, and there also seems to be a tremendous utility associated with it. The demand, I believe, is associated with a perceived utility, and as we get more and more data and just inundated by quote-unquote information. So it's going to wrap up our event for October, and next one's going to be November. Let me check the November. Let me check the date would be on that. It's going to be November 5th, it looks like. Oh, hopefully we'll have a smoother interaction with the video hangout, the video interface. I know I messed it up this month, but we'll just keep on improving and going forward. So, got any questions, Mary?
No, I don't think so, but thank you.
Okay, then. Well, take care and see you next month.
Good.